Great to see you again in this new video. In this new video related to basic structures, we're going to look into the uncountable set. Talking about before about the cardinality of sets, countable sets, and now we have to see what an uncountable set would be. Now, in computer science, in many cases, we deal with infinite sample spaces or infinite sets. Some of them may be discrete, and then we can say they are countable, and others are continuous, which means they are uncountable. Now we are going to prove that, certainly for the part that the continuous functions or sets are uncountable. But let's first have a look at the countable sets. When we looked at countable sets, we considered two possibilities. We have a finite set, like here the set A, which contains the elements 2, 7, and 9. And of course, this set is countable because it is a finite set. We can say there is a set and I can link each number to a natural number. But there are only 3, so it's basically clear that I can count them. Now, the other element, when we look at a set, let's say the positive odd integers, which is given by 1, 2, 3, 4, 1, 3, 5, 7, 9, and so on. This is also a discrete set, but in this case, the set is infinite. And what we can say here is that there exists a one-to-one correspondence with the natural numbers, which is given by f of x is 2n plus 1, with n between or starting from 0, 1, 2, 3, and so on. And the fact that we have that one-to-one correspondence, we can say that this set O of the positive odd integers is in fact countable. We can look at some other examples. We can look at the set of the positive integers, or z plus, which is 1, 2, 3, 4. Well, it is clear that there is a one-to-one correspondence with the natural numbers. Right? Z plus, depending if we take the natural numbers including 0 or not. Well, in this case, if we don't include 0 in the natural numbers, z plus would be the set of the natural numbers. And of course, there is a one-to-one correspondence with the set n itself. We also can look at the set of all the integers, and now it's a little bit more difficult because we have integers from minus infinity to plus infinity. It's again a discrete set, and we can build a sequence which can be created or for which we can define a one-to-one correspondence with the natural numbers, saying 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and so on. So basically, we also can define that one-to-one correspondence between the natural numbers and the set of all integers. Hence, we can say that the set of all integers is also countable. Now, when we look at the other sets, we can look at a special set, which is in fact the pairs of the positive integers. And we also want to know if this set is basically countable or not. Now, we consider the pairs of positive integers, which means 1, 2, and so on. So basically, a pair is given by a combination of 2 positive integers, which on themselves are countable, but is the set of the pairs of the positive integers countable or not? Now, we know that there are infinite possibilities. We know that the pairs are discrete. It's not continuous. So basically, we can already imagine, since the fact that we have an infinite discrete set, that this infinite discrete set will also be countable. It will have the same cardinality as the set of the natural numbers. What we can do is to construct an X and Y frame in which we put on all the intersections, the discrete intersections, the pairs indicated by, in fact, those circles. And now we have to create that sequence. And we can create that sequence when we draw this red line. We are bringing in the relationship, the one-to-one correspondence between the pairs and the natural numbers. And this is in fact clearly the proof that this sequence is existing and that it has a one-to-one correspondence with the natural numbers. So basically, we can create that sequence without missing any of those pairs that we have defined here. Now we can have a look at the set R. What can we say about the set R? Well, the set R is different from the set of the natural numbers because the set R is infinite. The natural numbers are also infinite, but in this case, the set R is continuous, which is different from the fact that the set of the natural numbers is discrete. Now let's have a look and let's consider that we have a set of real numbers which is given by the open interval 0 and 1, and this is a set of R. Now we're going to prove that in fact the set S is countable. We're basically going to prove that this is not true. So basically by contradiction we can say if the set S of 0 to 1 is not countable, then the set S has to be uncountable. And it also means that when a subset of a set is uncountable, the entire set is uncountable. Now, how are we going to do that? Well, we're going to look at a list of real numbers, and the real numbers Si, index I, are in fact members of this open interval. Cannot be 0, cannot be 1, but all the intermediate numbers can be there. And we write that Si is 0 point, and then we have the decimal elements, which is AI1, AI2, AI3, AI4, and so on. And we build a new number, also element of that set S, which I call S, and that number is 0.A1, A2, A3, A4. And how do we define A1 or AI? So basically we say that AI is equal to AI plus 2. So we take the decimal which has the coordinates or the index II, basically both indexes are the same. If that index is equal to 2, or if that decimal is equal to 2, then we add 2. If it is not equal to 2, we subtract 1. So basically we can define this. And when we look at the list here, we find for the first number, A11 is 2. So the first number, A11 is 2. It means that I will have here 2 plus 2, which is 4. For the number 2, we take A22, and A22 is equal to 8. It's not equal to 2, so we subtract 1. So we find 7. For the number 3, we look at S3. We look at A33, which is again 8. 8 is not equal to 2, so we subtract 1, which means that I find here again 7. For the fourth number, we have A44, which is 9, so it turns into 8. And for the fifth one, we have 3. It's not equal to 2, so it's 3 minus 1, which is 2. And basically, we find a new number, which is element of this set, 0.47782, and it continues there. But what happens is that whatever we do and whatever I am trying to make up, we can find that this number that we are building will always be some different number. And basically, it's somewhere in between. And I cannot create that sequence because whatever combination I take, I create a new number with infinite decimals. It is the fact that I cannot create that sequence. Every time I find a new number that will not be in the list that I've written, basically we have to find out that the set of the real numbers is uncountable because the open interval s from 0 to 1 itself is also uncountable. Basically, the set itself already counts an infinite number of elements. And it's also very important to look at some other very important point here, and it's related to the cardinality. Now, the set of the natural numbers is an infinite set. The set S, which is in fact the interval 0 to 1, is also containing an infinite number of elements. And that's more than the elements of the set of the natural numbers 0 and 1. So basically what we can see here is that even in this small interval of the natural numbers 0 and 1, we see that in the interval of the real numbers, that there are already an infinite number of elements. Now, we cannot say that infinite is more than infinite, that R is more infinite than Z. But what we can say here is that the cardinality of Z is clearly smaller than the cardinality of the real numbers. And basically here we are not saying which infinity is larger, we're talking about the cardinality of the sets, and we're comparing the cardinality of these sets. Now, when we look at the discrete sets, we can see that the cardinality is the same, while the continuous sets, the cardinality of those continuous sets is larger than the cardinality of the discrete sets. And that's a very important point to consider when we're looking at cardinality. Now, and also look at some results and theorems about cardinality to finish this video. First, we have the theorem about cardinality and the union of sets. Now, when we look at two sets, A and B, both of them are countable. In that case, we can say that their union, A union B, will also be countable. Now, their cardinality can be different, but that's not important. If we want to prove this case, we basically have to look into three cases. Basically four cases, but there are two cases which are in fact the same. The first case is where A and B are finite. When both are finite, it's clear that they are countable, and the fact that they are countable and finite, we can say that the union of those two finite sets will also be countable. Now, the second element, the set A, is finite and the other is countable, or B is finite and A is countable, or infinite. We can say this, in fact, or we can make this in one proof, in one case, where we can say that one of the sets is finite and the other one is infinite and countable. Now, the fact that infinite countable means that it is a discrete set, a set of discrete elements, and when we had a finite set to that, we will still have a countable set because we had two countable sets. We can still define that one-to-one correspondence with the natural numbers. The same we can conclude when both sets are infinite and countable. When both of them are infinite and countable, we have again a discrete set, which is the unification of A and B, and of course, finite and discrete means that the set will be countable also. Now we can look at another theorem. The other element that we can consider or important theorem is the Schroeder-Bernstein theorem. And the Schroeder-Bernstein theorem says that when we have two sets A and B, of which the cardinality of A is larger or equal than the cardinality of B, and the cardinality of A is smaller than or equal to B, then the cardinality of A is equal to B. This also means that there are one-to-one functions f from A to B and g from B to A, and that also means that there is a one-to-one correspondence between A and B. So basically, this is the theorem that states the relationship when we have this cardinality, the cardinality of A larger or equal to B, and the cardinality of A smaller or equal than B. In that case, they both have the same cardinality. So this was the video about the cardinality, the countable and the uncountable sets. And in fact, we're finishing this part of the course, and we will be talking into the next presentation about matrices. I'm looking forward to seeing you there. Thank you and bye-bye.